For organizing this wonderful event. Many of the folks over here have already thanked them for getting all of us here. I think actually they should be thanked for making sure that not more people are crashing in here. Just wonderful to see this huge turnout. So many old friends, so many young folks, and I'm really honored to be speaking over here. So I'm going to talk about low degree polynomials. So let's start with the obligatory birthday cake. So we all know Avi has a sweet tooth and some chocolate and some strawberries on top will obviously be sort of an essential prerequisite to a good talk. I also want to talk a little bit about a fascination for a different item that I think I inspired him into. So Avi, do you know what this is? That's a cheeseburger. So this is a talk that I gave 20 years ago. It's a cheeseburger again, and 20 years ago when I was giving talks, every talk had exactly the same content. I would start talking about low degree polynomials and then do something with them. And at some point I had to have sort of a story for why I'm doing the same thing. And I said, look, you know, this is like the Olympia restaurant in the Saturday Night Live, a television show that used to be popular in the 70s and the 80s. Where anytime you go there, whatever you want, you go there at breakfast, you go there at lunch, you ask for a soup, you ask for a salad, you want a chicken sandwich, you get a cheeseburger. Because that's all they can prepare. So this is all I can prepare. So I said, look, you know, what you're going to get is polynomials again. I mean, I don't know anything else. But the nice thing about this was actually Avi got addicted to this thing. He actually demanded cheeseburgers at times and said, yes, I like it. So, well, you know, Avi, happy birthday, you're going to get one more. All right, so yes, this talk is about polynomials. If anybody has seen any of my papers before, then you know that these are sort of, you know, these are the two questions that have dominated my life. How do you test them and how do you correct them? And I'll tell you about that and why. A little bit of history. And like I said, you know, people know that I was very closely involved, but actually Avi was a major influence in my involvement with these questions, and that's what probably I'm going to talk about a lot. And maybe I'll give you, just because Avi likes new stuff, I'll tell you one slide of new stuff, but really not much there. So it's mostly going to be a story about this one paper. This is a story of an insecure graduate student, 4th year of graduate school, second stock paper, okay? So not doing too well, but there were 5 people on this paper. Peter Gemmel over here and me were the graduate students then. Ronit had managed to successfully avoid the confinements of graduate school and was now a postdoc somewhere between Princeton and Hebrew University, where Dick Lipton and Avi Wigderson sort of joined in, and we managed to write this paper. I never read the title, not even today. I just cut and paste from the old slides. So this was the result. I mean, 4th year of grad school, you're trying, in Berkeley, there's something called this area exam or qualifying exam. We have to explain what kind of research you're doing, what you're planning to do, how do you think you'll graduate. Dick was on this committee, Dick Karp, and I sort of told him about some work that I was doing on online algorithms. Dick didn't buy it, and then I said, look, I'm going to solve these data structure problems. Dick said, you're not going to solve this. And he was right, I was wrong. So I said, look, okay, there's this paper, and by the way, you know, and so this paper basically got me to pass these qualifying exams. So this is quite, at that time I didn't realize it, but this was quite significant. The 2 results in this paper, and these are the results that are going to be the subject of this talk. Okay? It says degree D polynomials are something resilient and they're robust. In modern language, this would be they are locally decodable codes and they are locally testable codes. But, you know, so this is roughly what this talk is going to be about, and I'll try to tell you what we did in this work and what's been happening since then. So if you have a family of functions, degree D polynomials in any number of variables, could be this family that you're thinking about, we'll say that it's resilient with k queries, so order of D queries, and a resilience parameter which should be between 0 and 1. The higher this number, the more resilient the function is, the nicer it is. If there is some decoding algorithm which is given this, all right, let's do some video of this thing. Okay? So this is the definition from the previous slide. What does it look like? So I give you an arbitrary function in the family. So this is the set of degree d polynomials. So this is some polynomial of degree d. I've written down this truth table. And I'm saying, okay, I'm giving you a function which is not quite identical to that, but a few spots have been changed. These red spots have been changed. So I have a function g which is close in Hamming distance. And what I'd like to do is find out what is the value of that function at that particular location. Now, if I look over here, it's red, it's corrupted. I don't know what's red, what's green, but I'd like that value. I cannot just read it off from here, but this is all I have access to. So what I'd like is an algorithm which goes into this mechanism, makes up to k probes, and says, okay, look, here is the value that you're looking for. It outputs this. So that is a resilience. If you can do it with k queries and manage to correct a delta fraction of errors, then you're k delta resilient. Okay? Does this definition make sense? This is allowed to be probabilistic, and we want these things to be successful with high probability. Thanks. Everything will be probabilistic. Yeah. So we proved that polynomials were resilient with as many queries as the degree, which can be very small when the number of variables is very large. A degree d polynomial in n variables has exponential in d or n coefficients. So this is very small, was an important result. A second thing that we proved in the same paper was that degree d polynomials are also robust. Now, what is robustness? It's a sort of saying I have this global object, a function in n variables. I'm going to look at a very small piece of it, and I'm going to try to see from this local view how far is this function that I'm looking at from the family of functions that I care about. So I have a function which is supposed to be a degree d polynomial in n variables, but I have a very sort of a small view of it. It's the local view, and the local view should give me a very good estimation, or at least a lower bound on the global view. Okay? So that's what we expect over here. This is the definition that I'll come up with later. And we said that, look, again, once again, the first parameter is how local is this local view? How many things do I look at? And the second parameter says how good is this estimate compared to the actual global distance. Okay? So these are two things that we were looking at, and these are the two papers, the two results in the paper, or the two main ones that I wanted to talk about. So what was the background for this? This background comes from a very nice previous work of Lipton, about a year old at that time, saying that actually, firstly, polynomials are resilient, and this gave us a beautiful connection between worst case complexity, which we'd already been studying for many years, and average case complexity, completely unexpected at the time, and it came up by a very, very simple proof. We'll show you the whole result and the proof right now, and we'll talk about more variations. So he said that polynomials of degree d are resilient with order of d queries. So I'd have to look at this function in d places, and resilient to a 1 over d fraction of errors. Okay, so if I change the value of a function, so what does that mean? If I take the n by n permanent as my running example of a degree d polynomial where d is n, so it's an n by n matrix, I'm taking its permanent, it's a polynomial in n squared variables of degree n, then it's by looking at its value at about n places, I can reconstruct it correctly given any function which is computing the permanent not everywhere, but on 1 minus 1 over n fraction of the inputs. Okay? Take all possible matrices, let's say in some finite set. If you have an algorithm which is usually correct, 1 minus 1 over n fraction of the times, it will also be something that we can correct and get the value right everywhere. So average case, 1 minus 1 fraction errors on random inputs translates to worst case, everywhere correct with high probability. Okay? So this was a beautiful result, wonderful result. Let's take even a look at the proof, because we want to do some improvements on it. Our first result was saying that we can actually improve the resilience, and I want to tell you the story of that. So how do you, I'll just focus on the proof for the permanent, though the whole theorem is the same proof, but it's just useful to stick to one object over here. So suppose I have some function g, polynomial time computable function g, which given a random matrix computes the permanent with probability all but delta. So on Random matrices, the probability that you're wrong is at most delta, and this delta is at most 1 over n. Okay. Then we want to say that if I give you a particular matrix, not random but a worst case matrix, then it's actual, I can compute its value anywhere by this algorithm g sub r of 0. What is this g sub r? It takes, it looks at the value of the permanent of this function g at a collection of random matrices, individually random matrices, a plus r, a plus twice r, a plus thrice r, and so on, where r is something completely chosen at random by the algorithm. Okay. So you pick a random r, look at a plus r. Well, a plus r is a random matrix. G is likely to be correct there, etc., etc. So in fact, let's go through this analysis. I want to compute the permanent of a, but I'm going to look at this function, permanent of a plus I times r, for a fixed choice of a for a fixed choice of r. What do I know? Well, it's some function of I, and it's a polynomial of degree n in I, because it's a polynomial in degree n in all the variables appearing, but there is only one variable left. So you're left with a polynomial of degree n in this one variable. Now, if I look at any fixed choice of I in 1, 2, 3, and so on up to n, a plus I times r is some random matrix in the whole space. So by my assumption, with high probability g plus I r will be equal to permanent of a plus I r. If I have this equality for every I, then I have the value of this polynomial correct at n plus 1 places, but it's a polynomial of degree n. So I can actually, if I do the interpolation and say let's find the polynomial of degree n which agrees with little g at all these n places, I will actually get a polynomial which agrees with the permanent at these n plus 1 places, and that will be the right polynomial of degree n. Okay. So we conclude that if I manage to get all the n plus 1 values right, then I'm in good shape. Now it just remains to bound what is the probability with which I get all the n plus 1 values right. Probability that I get any one value wrong is at most delta. That's exactly the assumption. And the union bound says that the probability I get one of the n plus 1 things wrong is at most n plus 1 times this. Okay. Put all of this together, you get Lipton's theorem. Avichai? What happens if the field is small? Well, think field is big. Let's not worry about that today. It's a nice question, but it led to lots of interesting research later. All right. So that was the theorem. We wanted to improve upon this. So what can you do? And that was the main result in the first result that I was describing. So we said you can use error correcting codes to the rescue. So when you look at the set of values permanent of a plus I times r, when I ranges between not 1 to n plus 1, but let's say I goes from 1 to 10 times n, much more than I need, then I get the values of an evaluation of an error correcting code at 10 n places. And this is an error correcting code which can be decoded from a constant fraction errors efficiently. And in fact, these are the Reed-Solomon codes. I've done a lot of work on this since then. So we don't really need to get all the values correctly, because these can be corrected from a constant fraction error. So it's okay to get, say, 10% of the values wrong. So let's, instead of trying to get all the values right from 1 to n plus 1, let's just get 90% of the values right when you're enumerating over the 10 times n places. And why is this good? Because instead of doing a union bound on n plus 1 points, I can do a Markov bound on this thing, and you replace the union bound by Markov, you get omega of 1 from omega of 1 over n. Okay. So if you didn't follow the technical parts, it's okay. The story is when you use error correcting codes, you get this nice improvement. Rather than saying you cannot have algorithms which are correct about the permanent 1 minus 1 over n fraction of the times, and everybody is wondering what is n, what is 1 minus 1 over n, you say 90%. 90% is a nicer number. So, but the moral of this story is, in error correct, 1990s, error correcting codes are not, day-to-day elements of your conversation. These were not widely understood and used, definitely not algorithmically. There were probably a couple of entry points to this. One of those was the 1984 paper that Gil mentioned of Benor, Goldwasser, Wigderson. Another paper that mentioned error correcting codes in the acknowledgements was Goldreich Levin. But really this is not day-to-day conversation material. So let's in fact look at our paper. Here is the thing. Where is Dick Lipton? I guess he's not here, so I can't fix the focus on this thing. But let me try to highlight some things. So there we have, we have error correcting codes. We just saw a generalized BCH code. Okay, that's what we said, not Reed-Solomon codes which we all understand and use today, but something else. And there were all these mentions of the primitive nth roots of unity and so on and so forth. I had no idea what we were saying. We just put in whatever Avi told us to put in. This is what we had. Okay? This did get me into a significant amount of trouble. This was my first introduction to error correcting codes, at least the algorithmic aspects. I had no idea that you had algorithms to correct codes from errors. And so my thanks to Avi and Dick for introducing me to this wonderful area. Okay, so thank you, Avi. So like I said, these kinds of things, you just stick in whatever you want to stick in over there and you get your paper accepted to stock. Might work in other places, but here we had some trouble. Manuel Blum was not happy with this result. Now, Ronit's flown the coop. Dick and Avi are sitting in some other places. Pete Gemmell and I were the graduate students. We were left to face the music. And he said, what are these BCH codes? How do you decode them? What is the omega 1? Give me some good answers to these things. We looked at this paper and we said, look at reference 17. So I said, look, read reference 17. There is this book. And you can get a used copy for $700. By the way, it's kind of interesting to shop on Amazon for the maximum price that you can pay for a book. So he didn't like the answer, so we gave him a more refined answer. You just have to read these things, and didn't work. We had these conversations for a while, and after a while he said, go talk to Elvin. Elvin is Elvin Berlekamp, father of algorithmic coding theory, sat on the 9th floor of this building where we were on the 4th and 5th floors. So we went and talked to him. Now, I don't want to make this a talk about Elvin and Manuel and so on, but talking to Elvin can be a very interesting experience. There was a lot that went on then, but the moral was we actually did manage to learn a lot. We actually managed to improve the result, and we were able to prove that polynomials of degree d are actually half minus epsilon resilient. So if you have an algorithm which computes the permanent, 51% of the times this is as good as having an algorithm which computes it correctly everywhere. Okay? We did this by, if we had the guts, we would have called it how to decode the Berlekamp-Winchell decoder. This was a patent application. I don't know. I think they put in the maximum obfuscation that they could into the application. And then they gave it to us to read. It was not fair to graduate students. I wouldn't do it today. Maybe I would. So, by the way, 1991 we published this paper, but Avi was in Hebrew University. Dick was in Princeton. Pete Gemmell and I had never seen him. Okay. So Avi visited in 1991. By this time, the paper has already appeared. It has been presented, and I think, and in the meanwhile, Pete Gemmell and I had also sort of started working on this thing and got the resilience up from some constant to 49.9%, 1/2 minus epsilon. So I was very, very, very happy. I went up to Avi and I said, look, Avi, resilience is 1/2. And I can sort of, first thing I do is I introduce myself and say I'm Avi, and Avi says, oh yeah, let's see, I have these 70 stock papers. I have this 69th paper where I didn't meet all the authors, so you must be author number 4, and I have one more author to meet, he tells me. Like the only thing he said is, yeah, oh, that's one more to go. So he hasn't yet met Peter. So I say, okay, look, Avi, I have this resilience is 1/2, we can do this, Peter and I. So Avi says, great, now let's make it higher. I mean, all this work that we did, and Avi says, great, okay, let's do it. I mean, now, if you've encountered Avi since, there's an incurable optimist. Any theorem you want to prove, he says, of course, this is true. Like, fine. Avi, I can prove x. Great. Now let's prove x plus 1. He said, Avi, but I can also prove not x. He says, let's do not x minus 1. So, okay, so we, like, look, what do you want? We are optimal, okay? So I don't know if you know what is the sense by which I mean optimal. Some of you have probably heard this. And now we said, no, I want everything and you're not optimal. Let's go back. And so I said, look, Avi, I have to explain some things to you. If there are two polynomials which are both agreeing with this function in 50% of the places, which one can I give you? And this was sort of this model of unique decoding that we were working with till then, and that was the only thing I was familiar with. Well, I wasn't familiar with much before I had this paper with Avi, so it wasn't very surprising that this was the only thing I knew. But Avi introduced me to list decoding. I said, let me tell you about list decoding. And then, and not only did he say this, so he told me that, look, when you have two polynomials, you can ask, if you have two polynomials which agree on 50% of the places, you can hope to recover both. This was not written down in the books. There were some works in computer science maybe which talked about this concept, but it was not certainly widely understood and appreciated, and Avi just liberally sort of introduced me to this thing. Of course, it's not very great when you are out there and saying, look, I'm going to present you the optimal result, and he says, no, this is not optimal, go back. But it was very, very, very educational. It was much more than that, because he actually started telling me about some ongoing work which was happening in Princeton around Ronit and Dick and one of his students, Sigal R. And they said that, look, Sigal, Dick, and Ronit can recover both P and Q in this case. And so it was, okay, so I had to sort of go back to the drawing boards and figure out what should the next step in the problem be. I started talking to Sigal and Dick and Ronit, and eventually we came back, this is the damage report from what happened after the visit. So I said, look, actually, we ended up doing okay. We wrote a paper in which we said, look, if you have every time I compute the function, it either returns this polynomial p of y or returns q of y, two different polynomials, but it's always picking one of the two. Then we can actually report both of them. So you can't find which was the one answer which was right, but if there are two, I can find the two. So this was great, and this is also part of the wonders of personal communication. It turned out I'd actually misunderstood what Avi had told me, and Avi had said something which I interpreted to the best of my abilities. What he had said was, or what Ronit and Dick and Sigal had been looking at earlier, was the following question. So look at that difference if you can. I said if this member is contained in the set, but really what they were looking at was if this function was that set. So you know p of x and q of x, you just don't know the ordering. On every point, you're getting an arbitrary order. Somehow, this confusion and trying to understand what you would do here led to the algorithm for what happens when you have just the other thing. And this was fantastic for us. We got a Fox paper out of it, and so we were all very happy. But in retrospect, actually, it was much, much more useful than that, in the sense, firstly, I understood the notion of list decoding. I started thinking about it. Took another 4 years before I finally had a paper which said, look, actually, you can decode these codes, and these are, by the way, Reed-Solomon codes, not generalized BCH codes anymore, and you can decode them from a large fraction of errors, much larger than whatever we're mentioning here, and these became sort of food for more work that we did. The paper that I wrote here and with Guruswamy were univariate polynomials. Later with Salil Vadan and Luca Trevisan, we had multivariate versions of these things, and all of these combined to say polynomials are resilient to 99.9% errors. Okay? And the notion of resilience has changed because we are now in the so-called list decoding regime, an entire regime that I would not have been exposed to without Avi. And what it says is that, look, if I have a function and I have this function f, g, which equals some polynomial f with some probability. So does not equal with probability at most 1 minus 99%. If this quantity is 99%, then I can report 100 polynomials, one of which will be contain the one that is the correct one. Okay? So that's the notion of resilience, but it's as good as the previous one in the setting, and we were able to get to these results thanks to a collection of beautiful things. One, we had, when we started this line of work, and the first result that I mentioned, we had at least the graduate students there, we had no idea what error correcting codes were, what you could do with them. We learned about that. Then we learned that actually there's all this nice rich theory about it which can be sort of simplified into our language and used for constructively. And then we learned about new questions and then overall solve them. And all this because Avi was very actively interfacing these areas together, interfacing people together, and bringing questions from different areas together. This has been sort of one of Avi's formulas for success, I think, in many, many stages, and I definitely benefited from them. So thanks to Avi, so the many wonders of polynomials, to telling me about error correcting codes, for list decoding, and this, this curiosity and this optimism. Everything is true except if you prove it's not. And then, of course, it's obviously not true too. It's phenomenal. All right, so now I'm going to move to the second phase of the talk. This, so far, I've just talked about the first result in that paper. Now, let's talk about the second result. So what was the second result? It says something very similar. The first parameter is again the same. I'm looking at a multivariate polynomial, looking at this function. You're claiming this is computing the permanent. Is it even computing a degree n polynomial? Let me try to estimate that. And I want to look at this function in about n places and ask the question, is this really looking like a degree n polynomial? This result says that you can actually get a very good estimate on how far you are from the space of degree n polynomials by very local views. The locality is this parameter, and how good is the estimate is related by a factor alpha. Okay? If this factor is closer to 1, you are really close to a good estimation. The best you can get this parameter to be is 1. The local estimate is equal to the global estimate. And if it is much smaller than 1, then the smaller it gets, the worse your estimate, but it's still non-trivial. And already proving something like 1 over d cubed was non-trivial. This was the first result of this nature for degree, polynomials of degree greater than 1. For polynomials of degree 1, there was a previous result of Blum, Luby, and Rubenfeld, which was the basis of this part of our paper. Okay, so this is the kinds of results that we are talking about. And let me say a little bit, this is the part of the thing that I want to talk about. And why do this testing? And we didn't know the answer to this, So in those days, this is sort of like when Noam was saying, look, when you have a hammer and you go around looking for a nail, actually this was the kind of a case where we had a hammer and we just kept banging and saying, look, if we bang, maybe there's a nail somewhere out there. This probabilistically checkable proofs was some nail that was lying on the ground. We just managed to smash it with this hammer. Polynomials turn out to be the building blocks of complexity. At least in my view, I say, well, this is a legitimate view of the world. You can take very complex statements, like I want to prove that a formula in n variables is satisfiable, or a graph on n vertices is 3-colorable, which is, proofs of this nature seem to require n bits of information. But you can convert them into very simple statements, like constant size statements, about polynomials which are very complex. Once you do this translation, you're actually in much, much better shape. And I want to say a little bit about this, maybe by this analogy. Okay? So imagine you have to inspect a building around you. Okay? And you have this room, and you want to say, look, is this going to be structurally stable and hold, couple of hundred theoreticians? So what do? You could say, look, this building is composed of n atoms, and I'll go and inspect each one of these atoms and see if it's properly related to all the neighboring ones. Let's see if that works. sounds like you'll pay your inspector a lot of money. Okay? On the other hand, you can say, look, there's a constant number of walls in this thing. Let me do some generic structural tests on walls. I've got that done. And now let's see if the walls are properly aligned in this thing. Much simpler looking problem. In fact, probably this is what we usually do in inspecting buildings. We are not going around looking at each and every atom and seeing if it works correctly. Sort of we tend to assume that large self-similar structures are always done nicely. So the former view would take a lot of checking, the latter takes a lot less, but you have to be able to do checking of walls. This whole wall, I mean, is it structurally stable or not? You have to understand that. The nice thing is this is sort of bulk work. I mean, you can outsource it or something. So, it's something that you should be able to do, and this is exactly what happens actually in the world of complexity theory with polynomials. So the polynomials are the walls of complexity, and statements that you want to prove are typically the building blocks. So rather than saying I have a graph and I want to prove it's three colorable, etc., which sounds like a statement which inherently makes you look at the colors of every vertex and n different bits of information, you can say, look, here is a problem which is NP complete. There is a local map from polynomials to polynomials. It takes 4 polynomials and produces a 5th one. And I'm asking the question, are there 4 polynomials for which the output would be 0? Okay? And you can verify that fairly easily. This is the bulk testing the wall. Just look at each one of these polynomials and say, is this really a polynomial? And a second one which says, okay, let me pick a random value of the output and see if this polynomial phi evaluated on inputs A, B, C, and D of this R is actually 0, okay, for one random choice of R. This is sort of like saying, okay, I'm looking at the inspection between this wall and that, the relationship between these two walls. Is this a good one? I just look at the angle and say, look, is that going to be stable or not? And you can do this nicely because it's local, and the first part is something that we can, low degree testing, and this local testing estimation of distances of polynomials allows us to do. So just as a proof of concept, I'm actually going to tell you why you can assume that this local map can be NP complete. Here is the length of the proof. Okay? This is the reduction from 3 coloring to satisfiability to polynomial satisfiability. It's not long. Okay? I don't want to go through the thing. Here is a very simple proof that the whole thing, there is this one single map, only involves 4 polynomials. If you can find 4 polynomials which are identically 0, then so that the output is identically 0, then this is an NP complete task. Something as simple as saying is A squared plus B equals C minus D, etc., etc. Really, really simple thing, and it turns out to be NP complete, and that's the reason why probabilistically checkable proofs and local things are possible. So this brings me back to this local view of polynomials. So I would like to look at the space of degree D multivariate polynomials and try to see, can I check to see if they are, how good an estimate can I find? Somebody gives me this thing, says this is supposed to be a low degree polynomial, its degree is really n. Can I figure this out by making very, very local inspections? And we are saying, okay, we are happy with something like number of inspections depending on D, should not depend on the number of variables. I might even be happy to do D squared, but I would like to get a really good estimate how far we are from the space by this very local view, rather than looking at the D to the n values that would take to determine the coefficients, etc. Okay. So what these results in probabilistically checkable proofs, most of which happened, by the way, after all our work, actually says that the better you can make these testers, the better probabilistically checkable proofs you can get, and there are many of these works, one of which involves Avi as well explicitly, others involve students of Avi's. And by the way, one of the other very nice things that I have to thank for is people like Amir, like Eli Ben Sasson, and their students who have all been working on this problem with me and making my life so enjoyable. These are all former students of Avi and his descendants. So all these results are saying better testers are going to be more useful. So I'm going to tell you a little bit about what is known today. And I want to sort of stick, there are many, many parameters that you can try to improve upon. I want to focus on one thing: how good a robustness can you get? Can you make this robustness, higher and higher? Just like Avi wanted resilience from 1 over d to constant to 1/2 to 1, I would like to make sure that this resilience this robustness can also be pushed as close to 1 as you can. And some of these results explicitly say the closer the robustness gets to 1, the better the probabilistically checkable proofs you can get. Okay. So this question, and this brings me back to Avi, and here is a relatively unacknowledged debt. Both Ronit and I understand this very well. First, the first result which improved on the robustness was a result that I had with Ronit in 1992, where we said, well, it can go from 1 over d cubed to 1 over d. But this is a result where in the acknowledgements we say we thank Avi for suggesting this question and for giving us the hint on how to prove it. And the hint was the same hint that we used. Don't use union bound somewhere, instead use a Markov. I mean, it's a hint, anybody can give this hint. I can go tell any one of you who's using a union bound today to go use Markov. It works. In this case, it worked. It was it was a very pointed hint. And I would suspect he had seen pretty much all the steps. He just let us figure this out, but we got a very nice paper out of it. So thanks again, Avi. It was subsequently improved, and in fact, this is sort of essential to the PCP theorem, where we first got constant query complexity for PCPs to a robustness of 1, at least that particular proof. This was essential. And later works by Raz and Safra, Raz being one more person that somehow got influenced to work on these questions. And Aurora and I managed to get robustness very close to 1. Okay, so these are the sort of steps of progress that we managed to get over here. So this is roughly all the progress, but I would say a fair chunk of it sort of started in this work with Ronit. So we're really grateful to Avi for setting this off. There's this very nice thing that I could talk about, but it will take me a little bit more time than I want to, and I don't think I want to stop you from lunch. It's not a nice position to be in, but I do want to say one more thing. There are other reasons to test, and one of those was given by a beautiful work of Emanuele Viola, who is, I think, a visitor here or a postdoc here with Avi Wigderson. Really lovely result, one of these amazing conceptual things when you sort of look at this question, everybody's looked at it before, and came up with all kinds of ad hoc analysis, and this was like a 3-line proof, 1, 2, 3, and it worked. I mean, it was just really, really lovely. There are more works which are saying, look, we should study low-degree testing, and many of these times, the amazing thing is that these results have been discovered, these applications of low-degree testing were discovered after the low-degree testing theorems were found. So it's one of these cases where it has actually paid to go around hammering needlessly with this hammer and hoping somebody will end up looking like a nail. So this is just a very quick status update on what we know about low-degree testing. So quick reminder, this is the class of functions that we are interested in, polynomials in m variables whose degree is at most d, a total degree, over a field of size q. And we'd like to understand how well can you test this thing. Okay? So, and it's always useful to consider what is how good an error correcting code is this family of functions. This is a very well studied question. These are Reed-Muller codes. This parameter is very well studied in the literature on coding theory. What we'd like to understand is how does this relate to this robustness that you can get. And the state of the art is sort of basically summarized by 3 theorems that I'll mention. One of which says that if the distance of this code is really excellent, tending to 1, then the robustness is also going to be excellent, tending to 1. So really, you don't lose anything in this local testing. Locality comes for free. The second, this is a result due to Raz and Safra, and there's a variation due to Aurora and in some work of Aurora with me, but this, for example, is a concrete instantiation of what I mean by these kinds of implications. So a second theorem says, well, if I don't have such good codes, but they are codes of distance 10%, then you get some positive robustness. And this is something that was remarkable, that we'd been looking at this question for such a long time. We'd never articulated this possibility till recently. In fact, took some work with Elad Haramathi and Alan Guo, my student and Avi's grant student, where we were finally able to establish this fact. And once again, some very simple, clean looking statements can be proved about low degree polynomials. The final thing says, well, if you have codes whose distance is not really a fixed constant like 10% or whatever, it somehow depends on the parameters q and d, what can you do? Well, you can still go around getting robustness which is more or less dependent only on the original distance. And so there's a spectrum of possibilities. How good is your code depends how it influences how good is your robustness, and all of these theorems sort of put together give us a spectrum of the results over here. And this is another reference which tells you where this work happened. Okay. All right. So I won't talk about techniques, but there's really, like, over time what has happened in this field is also that used to be that we threw every sort of tool that we knew about into this thing, and by now we're sort of reaching the point where sort of we've gone over the hump and we're simplifying things, and there's really two different ideas that seem to be sitting together and coming together to prove these statements. So in that sense, I think things have actually become more nice in the space, but I won't have a time to go into those things. So instead, let me just once again conclude by saying, we are really, really happy to have had this collaboration with Avi, and thanks so much for contributing your generous ideas. I also have sort of, I love working with Amir, I love working with Eli, with Elad, with Nogar and Zui, and all of these sort of descendants of Avi, so for your students as well, and many inspiring moments and sushi and whatnot. Thanks very much.